give me a feeling for why the segmentation problem involves probability?
Okay. Fine question. Here's why. The segmentation we're going to deal with is of MRI images. Okay, that's the one I've chosen. That's what's typically taken. Those are images that are, someone has a brain tumor, and the image that best distinguishes different tissue is an MR image. Okay, and when you if you look at the physics of the MR, which I'm going to go over in a second, I'm going to give you an intuition for MR because maybe that'll be the only thing you'll remember from this lecture. But that's when you take an MR image and you want to look at what is, is pixel value 150 mean tumor? Okay, if that's what you want to figure out. When you look at the image, because of the way the MR process itself works, there's thermal noise, there's all sorts of other noise, you can never say that pixel value 150 corresponds to this structure. So all you do is you have a model of your process, which is a Gaussian, which is why we're going to talk about a Gaussian a lot. And so you model it as a probability density function. And you say that if, I'm going to make a Gaussian which has a certain mean, and then say that, okay, if a pixel value is 150, it has this much probability of being a Gaussian. Okay, but it's also allowed to deviate from that. Yes, or any structure. I picked a tumor. That's probably not the best example because tumors actually have the most wide range of intensity simply because there are many types of tumors. So a different structure, let me pick a different structure such as blood vessels. Okay, they're more consistent across patients. But because of the noise involved in the process, you can never say, in MR, you cannot say that this intensity corresponds to this structure. All you can say is that intensity values for this structure are a probability density functions about this mean and about this variance. That's why what you need to be able to do is, if you have that information that you model into your segmentation process, you do infinitely better than saying that, white matter is always going to be 130. Because what you'll do is you can take an image and add up all pixels that have value of 130. There'll be 5 of them, while white matter is supposed to, compose of at least 10%.
Do you use information on the location too?
Got these fine questions here. We're not going to use that here, but as I did in my PhD thesis, when I started working on this problem, the typical bias was that you really want to look at the intensities, and you say, does this intensity tell you what structure it is? And I hammered on that for a good 5 years. Because I figured that there are all these smart people, that's how they want to do it, and there must be, somebody must have a bug in their equation, so let me find it. And then as I was starting to do that, I realized, in fact, I was interning at Mitsubishi, which is right across the street, I think that way, at Merle one summer, and that's when I spent a lot of time that summer segmenting out, not brain images, but these were knee images, okay? They wanted to build an arthroscopic surgical simulator for which what they wanted to do is when someone's knee MR scan comes, they wanted to know where the bone is, where the cartilage is, where the meniscus is, and have a 3D model. So in the same way that I showed you brain here, that's what they wanted to do for the knee. Okay? So I started with the conventional approach. I built an intensity-based model for the bone, and it's a little bit trickier than a Gaussian. It ends up being a mixture of Gaussians, but that's a different story. And I spent the whole summer just trying to segment out knee, a bone, the femur, using an intensity model. End of the summer, and I was like, okay, all I've got is this big bone, which is so obvious in this image that it doesn't even seem like it's a big problem. And I had about a week left, and I really wanted to segment out cartilage, okay? And the only intuition I had at that point is that the femoral cartilage lies right below the femur, okay? I wanted to use that information. I couldn't care less what its intensity was, because in MR it doesn't even show up well. So what I did was I took 3 different scans of different patients, and I created a spatial model. So what I did for this cartilage, I went and I measured, if I know where bone is, what is the probability of cartilage being, at different pixels? Is that making sense?
Yeah, sure.
And I modeled that as another Gaussian. I said that, okay, I already know where bone is. I know where all the bone pixels are. From my previous scans, I figured out that, at a distance of 2, 3, and 5 pixels, the probability of being cartilage is very high, and it sort of starts to drop off as a Gaussian. Okay? And that led to a whopping number of publications. And that was a very simple idea that why don't you use spatial information? And it's become, people, the trick is encoding spatial information is not very easy. You can do simple things like distances. But usually structures, cartilage is a very nice example of it just hugs the bottom of the bone. When you start looking at tumors, for example, a tumor is not defined spatially. Now, it can occur anywhere. So if I told you that here's the ventricles, here are the blood vessels, here are the cortex, where's the tumor? What is the probability of this spatial location corresponding to tumor? You have no idea. So there are some problems where intensity is exactly what's going to get you the answer. But in a lot of other problems, spatial information is very, very important. We're not going to do that here. But if you decide to move into medical image processing, come talk to me. Yeah. So that's where, anyone else have any questions? I realize we went off, but he started it. So.
Just one
yes.
Thing, did you also use any intensity information for the cartilage, or did you?
Yes, I used both. And that was an example in which it was a nice example in which to show off the importance of spatial information, because cartilage intensity contrast is very poor in MR. But of course, if I wanted to give it a fair shot, I would have gone back and had a different acquisition done where the cartilage was nice and bright. But that wasn't my point. Yes.
Does the intensity, or rather, does the decision regarding one point affect your decision regarding a nearby point, for example, if you already made that decision?
I'm telling you, is this rigged? Or these are just fantastic questions. They have nothing to do with my lecture here, but these are the real issues. Once you move on, we're going to do some basic stuff here in this class. But that's a great question, because when you look at a pixel, if I tell you, you don't know anything about these medical images, I'm just going to tell you, this is a pixel here, and it's tumor. Okay? Do you know something? Can you tell me something about the 8 surrounding pixels? What if you have to put money down, what would you say the pixel above it is?
Depends on the intensity.
Yeah, if it's
right?
if the intensity is...
Or let's say you didn't know intensity, just prior probability.
Yeah.
Tumor, yeah? Right? Then you could also say, well, if I tell you it's a white matter pixel, white matter next to it, right? And as you move away from it, the probability is going to drop, right? So now in order to maintain the spatial coherence of labels when you do segmentation, is you build in what are called, you can call them spatial coherence priors. They're called Markov priors. And what they do is, as you're doing the segmentation becomes more of an iterative process. So what you do is you go off and you say, okay, now I'm just going to use only intensities to figure out what the probability. In fact, it's called what's the class conditional probability. We'll go into some of these. You've seen some of these terms before. We'll go into them a little bit more in detail, but the idea is you look at a pixel, you look at its intensity, and you have 4 Gaussians, which are telling you that, white matter is centered around 150, background is centered around 10, gray matter is centered around 50, and tumor is centered around 200. Let's say you had these Gaussians, right? So you would do the segmentation in that case in an iterative manner, and first say, okay, all I'm going to do is do the classification right now, the segmentation or the labeling, classification, these are all synonyms here, based only on the intensity. Okay? Then on the next pass, what you'll say is, okay, let me assume that this segmentation is good, but I want to induce some coherence of labels. So there are 2 adjacent pixels, one which has very high probability of being white matter, and then there's the next one which has sort of not very high, but good probability of being gray matter. White and gray are 50-50. I'm going to make it a white matter simply because it's right next to a guy who really strongly thinks he's white matter. Okay? So these are called Markov priors. And we're definitely not going to do them in this class. But and the reason people shy away from using Markov priors, typically what people will do is they'll build in what's called the independence assumption, which is that each pixel is independent. The reason for doing that is very simply that adding neighborhood information makes the computation, it's much higher, and there are tricks around it, and I worked on some of those simply because all these questions you guys are asking were exactly the questions that I asked, except it took me a lot longer to get to them. And it was very simply, okay, I have intensity now. Can I put in spatial? I have spatial, but can I put in local coherence? Because I wanted the segmentation to look smooth. Because these structures, they're naturally evolved structures. They're smooth. You don't see spurts of gray matter between white matter tracts. You tend not, those things don't happen in nature as much. So that's all of these all of these pieces of information, the only price is computation.